All right, let's talk about one of the absolute cornerstones of modern engineering, finite element analysis, or FEA for short. This is the tool that lets us see into the future of a design, to test it to its absolute limits, all before a single physical part even exists. So how does this digital crystal ball actually work? Well, let's dive in and find out. So picture this. You've just designed a really critical part, maybe for an airplane or a bridge, something important. How can you be totally sure it's not going to fail under pressure? I mean, you can't just build 10 of them and smash them all, right? That'd be way too expensive and take forever. So the real question is, how do you test a design when it's still just a file on your computer?
And the answer, of course, is finite element analysis. You can think of it like a virtual crash test dummy, but for literally any part you can imagine. It's like a digital laboratory where we can apply all sorts of forces, heat, vibrations, you name it, to a 3D model and see exactly how it would react in the real world. We can predict stress and find weak spots with incredible accuracy.
But this isn't magic, right? FEA is built on a really solid foundation of physics. To understand how it works, we need to look at the three core governing equations that make all these complex simulations possible in the first place.
First up, we've got equilibrium. This is a basic idea you might remember from physics class. It just says that for something to be sitting still and stable, all the forces acting on it have to cancel each other out. The pushes have to equal the pulls. This makes sure our virtual model is stable, just like a real object would be.
Second, there's strain displacement. So when you push or pull on something, it deforms, it changes shape. Strain is simply how we measure that deformation. The software calculates this for every tiny piece of the model, which is absolutely crucial for knowing if a part is going to bend too much or even snap under a load.
And the third piece of the puzzle is the constitutive law. For a lot of common materials, we use what's called Hooke's law. This is the key that connects the internal forces, what we call stress, to the deformation or strain. That E in the equation, that's all about the material stiffness. It's how the software knows that a steel beam behaves very differently than, say, a rubber band.
Now, just to keep things clear and simple for this explainer, we're going to make three basic assumptions. First, that the loads are static, meaning they're applied slowly without any sudden impacts. Second, that the response is linear, so if you double the force, you double the displacement. And third, that it's elastic, meaning the material bounces right back to its original shape when you remove the load.
Okay, so we've got the theory down. Now let's see how this all plays out in the real world, or, well, the virtual world. We're going to walk through a standard FEA workflow using one of the simplest examples you can think of, just a basic 1D bar getting pulled on from one end.
Pretty much every FEA project follows these 5 core steps. You start with your 3D model. You chop it up into small pieces. You tell the software how it's being held and what forces are acting on it. You let the computer run the numbers, and then, the best part, you get to analyze the results.
So, for our example, we're going to take this simple bar and run it through that 5-step process. Let's see what happens when we give it a good pull.
Step 1 is the model itself. We always start with a nice, clean 3D CAD model of our part. You can think of this as the perfect digital twin of the physical object we want to analyze.
Step 2 is where we create the mesh. And this is the really cool part. This is where the name finite element actually comes from. We take the complex geometry and we break it down into a whole bunch of simple, manageable shapes. These are our finite elements. Why? Because it's way easier for the computer to solve those governing equations for one tiny block at a time.
Step 3. Applying the boundary conditions. This is where we tell the simulation what's happening in the real world. So for our bar, we're going to lock down the left end so it can't move at all. And then we're going to apply a pulling force, a load, to the right end. Simple as that.
Step 4 is easy for us. We just hit solve. Now the computer does all the heavy lifting. It takes those 3 governing equations and applies them to every single one of those little elements in our mesh. It's just a massive number crunching phase that builds a complete picture of what's happening inside the part.
All right, the solver has done its job, and now we get to the payoff. Step 5 is all about taking those millions of numbers and turning them into something we can actually understand. This is where data becomes real engineering insight.
First up, let's look at a displacement plot. This colorful heat map shows us exactly how much the bar is moving. And it makes perfect sense, right? The fixed end, in blue, has moved 0. And the end we're pulling on, in bright red, has moved the most. It's a fantastic visual that shows the bar stretching along its length. Next, let's look at stress. This is a plot of something called von Mises stress, which is a really common way to see the overall internal forces happening inside the material.
Now, for this simple bar, the stress is uniform all the way across, which is exactly what physics tells us should happen. And this number, this is the critical one for telling us if the part is going to break.
So we have this stress value. What do we actually do with it? We calculate something called the factor of safety. It's a really simple idea. You just take the material's known failure point, its yield stress, and divide it by the stress our simulation just found. If the result is 2, it means our part is twice as strong as it needs to be. Awesome. But if it's less than 1, well, that's a huge red flag that it's predicted to fail. It is a vital metric for any designer.
So we have our results, we've even calculated our factor of safety, but we are not done yet. A simulation is just a prediction, and any good engineer knows you have to ask the most important question. Is this prediction actually correct? Verification is absolutely key.
So how do we double-check our work? Well, a few ways. First, we can check the reaction forces at the fixed end. Do they perfectly balance out the force we applied? They should. Second, we can do what's called a mesh convergence study. Basically, we make the mesh finer and finer to see if the answer changes. And of course, we can even compare it to good old-fashioned hand calculations. This is how we build real confidence in our results. And that really brings us to the main takeaway. FEA is an unbelievably powerful tool that has completely changed how we do engineering. But the software, at the end of the day, just gives you a number. What makes that number truly trustworthy? It's the engineer's understanding of the physics, the careful setup, and that critical final step of verification. The real power isn't in the software itself, but in the mind of the engineer who knows how to use it right.